Hello everyone, welcome to my channel. In this lecture, we will discuss about the separation of hydrogen from hydrocarbon mixture. So we will discuss the adsorption of hydrogen gas from the hydrocarbon mixture. So first of all, we will open the Aspen adsorption. This is the Aspen adsorption uh, window. You can also open it from your start menu. So Aspen adsorption, click on this one and it will open. Okay, it is already open. So first of all, I will add the component. So there are three component. In the gaseous mixture, there are three component. One is hydrogen, the second one is methane, and the third one is carbon monoxide. So we will separate the hydrogen gas from carbon monoxide and methane gas. So first of all, add the components. So click on the component list. Double click on the component list and click on the configure property. So here, click on use Aspen property system and click on edit using Aspen property. Click on this one. So the Aspen plus window will open. In that Aspen plus window, we will add the components, which is the hydrogen gas, the methane gas, and the carbon monoxide gas. So after that, we will add the property package, which is the Pin-Robinson equation of state. So it will take some time. Now this is the S1 plus, and this is S1 plus. So click on this component and the component list, this window will open. The component ID, the type, component name, and so click here, add the component. The first one is the hydrogen. We want to separate hydrogen from the carbon monoxide and methane mixture. So these are three are the component. There are various component in the hydrocarbon mixture like the hydrogen sulfide, ethane, and some other carbon dioxide and some other gases. So for simplicity, we will add these three components. So after that, click on next. So here you can see the method filter best method. So I will use the Pin-Robinson equation. This is the Pin-Robinson equation upstate. Click on that one and click on next. Here these are the binary interaction parameter. So here these are the KAIJ, KBIJ, KCIJ, etc. So these are the interaction parameter. Click on next and click on OK. So now click on the Aspen adsorption and click on OK. Now click on yes, and these are the binary interaction parameter in the Aspen plus. So it will close and the Aspen, this is the Aspen adsorption. Now you can save your file because sometime it crashes. So I will save. Click on save and I am name it the hydrogen adsorption. So in this lecture, there will be two type of adsorbent. One will be the zeolite-5A and the second will be the activated carbon. So now after adding the component, click on the default and add these three components to this component list. So click on double arrow and click on arrow. So it is added to the Aspen adsorption. The components are added to the Aspen adsorption. Now add the feed stream, the bed, and the product stream. So here you can see this ribbon. Here you can see the feed gas. These are the gases. So this is the feed gas, etc. So click on the arrow, the feed gas, and this is the bed. Here you can see this is the gas dynamic model. So this is the dynamic model. You can also add from this library. Click on the library, click on the add sim, and click on the gas dynamic, and here you can see the gas bed, the gas feed, the gas product, etc. And after that, here you can see there are the material type. So this is the material gas material connection, gas material connection here. So you can either add the material stream from this side, or you can use this ribbon. So for simplicity, I'm using this bottom ribbon. After that, add the gas bed. So this is the gas bed. This is the gas bed B1. By default, its name is B1, and this is the gas product. This is the gas product. Okay. This is the gas. This is the feed. So you can rename. Click on this one and rename block. So here we will rename it the gas feed, or simply just feed. This is feed. This is the adsorbent layer or adsorber. Rename block adsorption column. So it is adsorber or adsorption column. So this is the feed adsorber, and this B3 is the product stream. Rename block is the product stream. So here now click on this connection. This is the connection. So here this is a gas material connection stream. These are the gas material connection. So we will click on gas material connection, and here we will connect material stream with the bed. So connect this one, connect the product stream with the bed. So this is the feed, this is the stream number 1, stream number 2. Okay. Now, okay. Now the feed. So the feed, what will be the composition of feed? So double click on the feed. Double click on the feed. And here it is the model type is reversible pressure setter, and the enable reporting is true, and the flow unit is mole. Click on specify. Here the molar flow rate of the feed stream is 5 multiplied by 10 raised to power minus 6 kilomole per second. Okay, and it is free. It is free. It can changes inside the bed. And the mole fraction of methane is this one, carbon monoxide is this one, hydrogen is this one. This is the temperature of the feed. This is the pressure of the feed. So these value are given in this. We will add the value from this book, the Aspen Adsorption. So the feed. So we will add the feed composition. So in this, so this is the feed block. Here the mole fraction of methane is 30% methane, 10% is carbon monoxide, and 60% is hydrogen. And the molar flow rate is this one. The temperature, this is the pressure is 10 bar. So 30% is methane is 30%. The feed consists of 30% methane, 30% methane, 10% carbon monoxide, and 60% is hydrogen. 60% is hydrogen, and it is the feed is at 298.15 Kelvin, and the pressure is 10 bar. Okay, this is the feed specification. Okay, here you can see this is the feed specification. Now set the product pressure. So here the product pressure is this one. The temperature is also constant. It is a isothermal process. So the product temperature and the feed temperature will be same, because this is a isothermal process. So now close this one. This is the feed stream. Close this one. Click on the product stream. Double click on this one, and here click on specify. Now the molar flow rate of the product stream is this one, and the temperature is also same as the feed temperature, but the pressure is 1.01 bar. 1.01 bar. The temperature inside the bed is changes as the feed flowing inside the adsorption layer. the temperature will be changes, but the temperature will be constant. Okay. Now click on the bed. Double click on the bed. Okay. Number of layer within the bed. There will be two type of adsorbent inside the bed. So we will add the two here. There will be two type adsorbent. So we will add two inside this block. Number of layer within the number of adsorbent layer within the adsorber. So there are two. The adsorption column is in vertical direction and the spatial dimension is one dimensional and there is no heat exchanger inside this adsorption column. Okay. You can also description. One is the first layer will be the zeolite-5A, the second layer will be the activated carbon. So double click on this one. Okay, so here you can now close this one. Here a number of layer, this is two. Okay, okay, there are two. The bed type is vertical. Okay, number of layer is two. Okay, okay, now click on this one. Click on this one, and here the discretization method. So okay, okay, close this one. Layer number one and layer number two, vertical. Okay, so vertical number of layer is two. There are two layer. Okay, this is the layer. This is layer number one. This is layer number two here. So layer, click on layer number one. Layer number one, which is nothing but the zeolite-5A is present in the layer number one. These are the adsorbent. Zeolite-5A is adsorbent which can use to remove hydrogen or some other flue gases from the flue gas mixture. Okay, this is now this is layer number one, and the configuration block for layer number one is this is the general. So the discretization method for layer number one is given in this in this example. So here there are two layer or one dimensional. Okay, the discretization method for layer number one, for layer one is CDS2. CDS2, second order central difference scheme, CDS2 mean. So and there are 16 number of node CDS2. So we will use the discretization method to be used for layer number one is CDS2, and number of node is 16. 16. Okay, same as node number one. Okay, okay, it will take some. Okay, now click on the momentum balance. So material balance assumption and the momentum balance assumption. So for material balance assumption, we will use the what which type of equation we will use, the convection with constant dispersion, and for the momentum we will use the Ergun equation. So convection with constant dispersion. So material balance assumption, for material balance assumption we will use the convection with constant dispersion, and for the momentum balance we will use the Ergun equation. Okay, this Ergun equation is used to show the pressure difference at the inlet and outlet position of the adsorption column. So this is the Ergun equation, and this is the kinetic model. So the film model assumption is solid and the kinetic model assumption is linear resistance, lump resistance, and the form of lump resistance model is linear. Form of mass transfer coefficient is constant. Okay. The isothermal. So by isothermal for layer number one, which type of isotherm will be used? So we will use the isotherm for layer number one. Here the convection with constant dispersion, Ergun equation, and this is the film model assumption is solid, linear, lump resistance, and linear. Mass transfer coefficient is constant, and the extended Langmuir isotherm will be used for the isothermal model. So extended Langmuir 3, extended Langmuir 3 isothermal model will be used. So we will use the extended Langmuir 3, extended Langmuir 2, extended Langmuir 3. Okay, And the isothermal dependency, it depends on the concentrate, partial pressure. So, and the model depend on the partial pressure of the gas iso. The partial pressure of hydrogen, carbon monoxide, and methane. So, it depend on the partial pressure of the gas iso. So, this isotherm depend on the partial pressure of the gaseous mixture. Now, in the energy balance, we will use the what type energy balance. So, for the energy balance, we will use uh, non-isothermal with gas conduction. So, non-isothermal with gas conduction, non-isothermal with gas and solid conduction, non-isothermal with gas conduction. Okay, okay. And consider heat of adsorb base. It is non, and the form of gas thermal conductivity based on axial dispersion is okay. And the heat transfer to the environment is adiabatic or rigorous. So this is rigorous. Okay, rigorous based on axial dispersion. Okay, okay, okay. Now this is for layer number two. Okay, this is okay. Now this is the reaction. There is no reaction, and this is the procedure. Okay, there is no reaction inside the adsorber. So close this one. Now go to the bed number two, layer number two, inside the adsorber. So click on layer number two, and here we will use the discretization method. Will be CDS2. It will be the CDS2, and number of node will be 20. CDS2 and number of node will be 20. The momentum balance will be same as for bed number 1. Convection with constant dispersion. The momentum balance assumption is Ergun equation, and the material assumption is this is convection with constant dispersion. The kinetic model is same, and the isothermal is also the extended Langmuir 3. Yes, extended Langmuir 3 model. Extended Langmuir 3, and the concentrate depend on the partial pressure. Okay, and the energy balance assumption is also same as for layer number one. So non-isothermal with gas conduction, and the heat transfer to the environment is rigorous. So this is the rigorous heat transfer to the environment. Okay, there is no reaction in layer number two, and procedure. Okay, now specify layer number one. So click on layer number one and click on specify. So here you can see the thickness or the height of the adsorbent layer, the wall thickness used for the bed, and the internal diameter of the adsorption column, intraparticle wide edge, intraparticle wide edge, bulk density of the adsorbent. Okay, and the mass transfer coefficient for methane, carbon monoxide, hydrogen, and this is the constant dispersion coefficient for methane, carbon monoxide, and hydrogen, isothermal parameter, etc. So we will fill this table for layer number one. So the table for layer number one will be okay. So this is the data shared between layer 1 and layer 2. These value will be same for layer number 1 and layer number 2. The bed height is 0.5 meter. Bed height is 0.5 meter. 0.5 meter. The wall thickness for the adsorption column. The wall thickness is the bed wall thickness is 0.00134. So 0.00134 meter. Okay, meter, and the internal diameter of the adsorbent layer is the bed diameter is 0.1855. 0.1855. The interparticle wide edge is Okay, interparticle voidage, there is no information, so it will be present in the other table. Interparticle voidage for layer number 1. This is the interparticle voidage for layer number 1 is 0.61. This is layer 1, which is the zeolite-5A, and this is the activated carbon. So the interparticle voidage is 0.61. Interparticle voidage 0.61. Interparticle voidage is 0.61, and the intraparticle voidage is the intraparticle voidage is 0.433. 0.433, and the solid bulk density of the adsorbent bulk density of the adsorbent is this one. The particle density 850 kilogram per cubic meter. The adsorbent particle radius is 0.00115. 0.00115 meter. Okay. It is a spherical particle. Okay, sphericity is 1, and the constant mass transfer coefficient. Constant mass transfer coefficient. The constant mass transfer coefficient. Mass transfer coefficient for carbon monoxide, and this is methane and hydrogen. So constant mass transfer coefficient for carbon monoxide is 0.15. So we will carbon monoxide, it is and it is in 1 divided by second. Okay, per hydrogen it is 0.7. 0.7. For methane, for methane it is it is 0.195. So we will copy and paste it. Okay. Now the constant dispersion coefficient. So it is convection with constant dispersion. So the dispersion coefficient. So here you can see this is the solid phase heat capacity, the dispersion coefficient. So the dispersion coefficient, it will be present in table number. The dispersion coefficient. Okay. The dispersion coefficient for layer number 1 and layer number 2 for all components are this one. 1.5 multiplied by 10 raised to the power minus 5. This is the dispersion coefficient for all component in the two layers. So we will copy it and paste for methane, for carbon monoxide, for hydrogen. And the isothermal parameter for methane in layer number 1 is the isothermal parameter for methane in layer number 1 is this is layer number 1. Okay. Isothermal parameter for methane in layer number 1. This is layer number 1. Remember, this is layer number 1. So the isothermal parameter for methane layer number 1 is this one. This one. Layer number 1. This one. This is for methane. We will copy it. We will paste it. For carbon monoxide, it is copy it. Paste it. For hydrogen, copy, paste. Okay. Isothermal parameter. Isothermal parameter 2 for methane. This is isothermal parameter 2 for methane. Coffee. Yes. And this is for carbon monoxide. Carbon monoxide. And for hydrogen. Coffee. First, isothermal parameter 3. So for methane, coffee, methane, coffee. First, carbon monoxide, carbon monoxide, hydrogen, coffee. So coffee and first all values. So thermal parameter 4 for methane is 1159, 1159 for carbon monoxide, oxide, hydrogen is direction is 0, and this value is in megajoule per kilogram into Kelvin. The adsorbent specific heat capacity. Adsorbent specific heat capacity. So the adsorbent specific heat capacity. So here you can see the adsorbent solid phase heat capacity. This one, and it is in megajoule per kilogram into Kelvin. Okay. So we will use, and this is for layer number 1. So the adsorbent specific heat capacity. Coffee and waste, and it is in megajoule per kilogram into Kelvin. Okay. This is the wall specific heat capacity. The wall specific heat capacity. So the wall specific heat capacity. The wall, the adsorber wall specific heat capacity. So the adsorber specific heat, the adsorber wall specific heat capacity is wall specific heat capacity is wall material heat capacity is in megajoule per kilogram into Kelvin, and this will. So wall material heat capacity is this one. Okay. Megajoule per kilogram into Kelvin. Okay. This is the delta H, the enthalpy change for methane, carbon monoxide, methane, and hydrogen. Enthalpy change megajoule per kilomole. Constant of heat of adsorption. So this is the enthalpy change delta H. So for methane it is this one. Heat of adsorption for methane is 20.92 minus gigajoule per kilomole gigajoule per kilomole. Okay, for methane, carbon monoxide it is 22.175. Okay, for carbon monoxide, and for hydrogen it is 14. So it is for hydrogen is 11. Copy and paste this value here. Okay, and this is the heat transfer between wall and ambient. Ambient is 25 degrees centigrade outside the adsorber. So the heat transfer coefficient between wall and outside in megawatt per meters per square meter into Kelvin. So this is the heat transfer coefficient between wall and ambient. The transfer coefficient between wall and ambient. Wall environment heat transfer coefficient is this one. Megawatt per square meter into Kelvin. Copy, paste this one, and the constant of heat transfer coefficient it is 1. It is okay. Now the constant of heat transfer coefficient between gas and wall. Constant of heat transfer coefficient between gas and wall. So the fluid solid heat transfer coefficient. Fluid solid heat transfer coefficient wall is 1. This is the heat transfer coefficient. Fluid wall heat transfer coefficient. So fluid is gas. Gas is a fluid. So fluid wall heat transfer coefficient will be. So this is the heat transfer coefficient gas and wall. This one. And the constant for gas phase heat conductivity. Gas phase heat conductivity inside the adsorber. So thermal conductivity is this one. Gas thermal conductivity is 1 multiplied by 10 to the power minus 20. Wall thermal conductivity. So this is the wall thermal conductivity. Wall thermal conductivity is megawatt per meter into Kelvin. Wall thermal conductivity, wall density, the adsorber wall density is this one, 7,830 wall density. Okay, and this is the constant for gas phase heat conductivity. Gas phase heat conductivity. Gas phase heat conductivity. There is no information, so we will leave it. Okay. Now ambient temperature is 25 degrees centigrade, 298. Okay. The specific surface area of adsorbent, specific surface area of the zeolite. So the specific surface area of the zeolite, it is specific surface area of the zeolite is surface to volume ratio to this one. This is for the zeolite. Okay. And paste it. Okay, it is 2600. Okay, now close this one and close this one. Now this is the layer number 2. Add the same information. Click on specify and add all the information as we enter for the adsorb for layer number 1. So we will add the information for layer number 2 as we added for as we have already added for layer number 1. But remember the specific surface area, the adsorbent particle density, some value will be changes as it is given in the this table. So the particle radius and some other things will be other material parameter will be changes. So now I will edit all the information. I will pause the video and I will add all the information for layer number 2. So the particle radius. So this is the specification table for layer number 2. Here you can see the height of the adsorber column, the wall thickness, the internal diameter of the adsorber, the intraparticle voidage, interparticle voidage, bulk density, the particle radius, the mass transfer coefficient for methane, carbon monoxide, and hydrogen, the constant dispersion coefficient, and the delta H for the methane, carbon monoxide, and hydrogen, the isothermal parameter for methane, carbon monoxide, and hydrogen, etc. Here you can see the specific heat capacity of the adsorbent, the wall specific heat capacity. Remember these two are same for layer number 1 and layer number 2 because the adsorption column is same. Material of construction for the adsorption column is same for both layers. So this is the delta H for methane, carbon monoxide, hydrogen, the heat transfer coefficient between wall and ambient temperature and outside the adsorber is this one, the heat transfer coefficient, and this is the thermal conductivity, etc. The wall thermal conductivity, the wall density, etc. So the wall density for layer number 1, this is different because the specific surface area of the activated carbon is different from the specific surface area of zeolite-5A. So now this is close this one. Okay, close this one. Now go to layer number 1. This is layer number 1 and here you can see this is layer number 1 and click on initial. Here you can see this is the initial. Okay, close this one, close this one, also close this one. Now this is the file, this is the edit view, this is the tool. So here this is the tool, and this is the find variable, etc., estimation, etc. This is the flow sheet, and this is the check and initial. So click on check and initial, click on okay, close this one, click on the adsorber. This is layer number 1. So here click on the initial. So initially the methane was it was 10%, 60% hydrogen, 30% methane, 30% methane, 60% was hydrogen, and 10% was carbon monoxide. Okay, close this one. Now go to layer number 2 and click on initials. 30% methane, 10% carbon monoxide, 60% is hydrogen gas. Okay, close this one, close this one, close this one. Go to the flow sheet. Now go to the flow sheet, click on check and initial, and click on yes. So now it is ready. Now we will plot the breakthrough curves. So click on this button, new form, and breakthrough curve. Click on OK. This is the breakthrough curve. Now click on the product, double click on the product, click on the result. We will plot the results. This is the results. Okay, results. This is methane, drag and drop, carbon monoxide, drag and drop, and the hydrogen, drag and drop. So what will be the behavior of the mole fraction of methane, carbon monoxide, and hydrogen inside the adsorption column with the passage of time? It is nothing but the breakthrough of methane, carbon monoxide, and hydrogen inside the adsorption column. So now double click. This is the time axis. X-axis is the time. So the axis range is from 0 to 10. So I will change it from 0 to 400. Suppose 400, and the grid interval. The time window is okay. 400. Okay. 0 to 400. Okay. So this is 0 to 400. Okay. Okay. Close this one. Close this one. And this is the breakthrough. Now go to the, this is the, here you can see, click on this one. This is the run option. So the time now is 0, and we will pause our simulation at 400 seconds. So time is 400 seconds. Pause at 400 seconds. Okay, and it is in dynamic. So this is the dynamic. Dynamic is okay. Now click on the run option. So it will take some time. It will take some time to start the simulation. So here now you can see, this is the time. So the run is complete. Here you can see, this is the 400 second time. Now we can double click on this one, and we will decrease the time because this is the constant Here it is constant after 100 second. So I will use the 100, 120 suppose. Okay, 120, but I am changing it to, for example, to 50 second. Now, what will be the behavior after this is 20? Will be the 20, 20. Change it to 10, 10. This is 10. Now here you can see this is a 10-second time. Okay. Now here you can see that the mole fraction of hydrogen is increases. At 1 second it is increased to 75, 76%, about 75%. The mole fraction of hydrogen is increased inside the bed to 75%. And here you can see the methane concentration is decreased. So the methane is decreased, and the adsorbent inside the adsorber adsorbed more and more hydrogen at 1 second. It is more and more hydrogen. But the here you can see that the concentration of okay, the this is the concentration of hydrogen is increased, and the methane, and this is the okay, the methane and the other, this one, the carbon monoxide is slightly decreased. Here you can see slightly decreased inside, at the outside, at the outlet, at the product. The concentration of hydrogen is first it is increased, then decreased in the outside product of the adsorber. And here you can see that the methane is first it is decreased, then increased, and it is first in decreased, then increased, and here it is almost constant. First it is decreased, then it become constant, the carbon monoxide. So here you can see that after 1 second the hydrogen concentration is decreased. It is decreased. Hydrogen is adsorbed inside the adsorption column after 1 second. So this was all about that how hydrogen can be adsorbed inside the adsorption column by using the activated carbon and the zeolite of 5A adsorbent. Thank you very much for your attention. If you are new to the channel, please like and subscribe. Thank you very much.